Okay, hello all you crazy people out there. My name is Michael. I like wizards and dragons and making games. Welcome back to 3D Collisions in GameMaker. Last time I went and implemented a little data structure on triangle meshes that will allow us to do collision checks against them much faster than by just checking each triangle individually. And today we're actually going to be making use of that. So last week was octrees. As usual, standard disclaimers apply. This is part of a long-running series of 3D Collisions in GameMaker videos that I've been making. If you have not seen any or all of the previous videos, I recommend going back and doing that because this is going to build on a lot of it. Let's get started. So this is what our octree structure looks like up close. You can see, I really like how this looks visually. I don't know if I'm just weird or not. The code for the octree looks something like this. The important part is subdividing it into pieces so we can split an octree to a certain depth. Today we're going to be mostly ignoring that. In fact, I think I will go back to a single pane code editor, and we're going to actually be using this to implement collision checks. So the high-level goal of an octree, and indeed most other collision data structures that you can use, is to eliminate triangles from collision checks if you know that you do not need to collide with them. And for example, if you know that a 3D object is only going to collide with a tiny corner of a triangle mesh, octrees allow you to only check for collisions with triangles that are actually in that corner. This is why we sort them into the hierarchy. And the first step towards figuring out which triangles need to be checked for collision against an incoming object involves figuring out collision checks with the octree itself against the incoming shape. Just as splitting an octree involved recursion, we can also use recursion to figure out which inner octrees are colliding with the incoming object. I'm going to be going with the collision sphere just for now. But in this particular case, I personally think an iterative solution is more than adequate. Recursive solutions for this sort of thing exist, and if you really like recursion, you can go and do that, but I'm just going to be using a good old while loop for this. So let me start off with an array. I'm going to call this array process these. And it's going to be initialized to not an empty array, but it's going to be initialized to one element. The element is going to be our root octree. If you like, you can use a DSQ for this, because we are going to be treating this like a DSQ, but I'd like to use the built-in GameMaker data structures as little as possible for this. I think I actually haven't used any at all. Yeah, no hits in this entire code for any GameMaker data structures. Anyway, we are going to do a little while loop, and that is going to be while array length is greater than 0. Then we're going to do something. This is a while loop. This is going to run for as long as this array has elements in it, or until a collision is detected. If you are not careful with this, and if you do not write this code correctly, you can end up with an infinite loop, so be careful with that. First, I'm going to say our tree is going to be process these stored at index 0. We are more or less going to be treating this array as a queue. We are going to add values onto the end of it, and we are going to remove values from the beginning of it. So we are going to get whatever element is at the front of the array, and we are going to save it to this variable of our tree, and then we are going to array delete a value in the array process these at index 0, and we are just going to delete one element. So depending on whether or not this tree that we're getting from this the first position in this array actually contains other octrees, whether or not it's a parent node, or whether it doesn't, whether it's a leaf node, we're going to do different things. So if tree.children equals undefined. So if this is a leaf node in data structure parlance, and this if this octree does not have any more subtrees, we're going to do one thing, else we are going to do another thing. I'm going to start with the else condition here, just because I think it makes a little bit more sense, because it's going to involve pushing the subtree onto the list of octrees that we want to process. To do that, we are going to loop over each of the I is less than 8, I++. To do that, we are going to loop over each of the inner children trees. We are going to say if tree dot children index I dot check sphere with the incoming sphere. Then we are going to array push onto the process these array. We're going to push tree dot children index I. So if this particular branch, if this particular subtree is also in collision with the incoming shape, then it is possible that there are triangles within that subtree that are colliding with the incoming shape, and therefore we want to save it to the array so that we can process it later. These nodes that we are pushing onto the octree have the potential to contain triangles that are colliding with the incoming shape. Otherwise, if the subtree that we're checking does not contain any child nodes, we are simply going to loop over for our I equals 0, I is less than array length, and just like in the last video, I should probably mention I am not writing perfect machine code optimized code here. I am writing code that I think is easy to read and easy to figure out what it's doing. Writing 3D collision systems in GML is definitely one of the rare places where micro-optimizations can actually make a difference. I am increasingly interested in making another video in the future that's just about micro-optimizations on this code, but that is for a day that is not today. Anyway, we are going to loop over every triangle in tree.triangles, I++, and then simply we're going to check each of these triangles for collision with the incoming shape. If tree.triangles index I.check sphere against the incoming sphere, then, well, that's a collision. Our job is done here. We can return true. And if by the end of this big giant while loop no collisions have been found, that means that no collisions exist to be found here, and we can return false. Okay? So let me run the game now, and let's see if I actually got this all correct on the first try. Sphere is going to be shape 1, and that said check sphere variable not found before reading it, and I believe that is because instead of using tree.children.checksphere, I need to do tree.children.checkbounds.checksphere because this is an octree object. That's one of these. This does not contain a checksphere method, but the bounds is an axis align bounding box that does contain the checksphere method. Let me try that again. All right, so we're going to create one of those. One is a collision sphere. Right off the bat, we have shapes overlap being detected. If I were to move the collision sphere out, we can see that right about here, and I can't get it pixel perfect because I don't have a high degree of precision over where the sphere moves, where these shapes move, but we can see that about here, the collision stops being detected. On the other side, same distance, collision stops being detected. If I were to, what's my controls? If I were to move the camera out a little bit and move the sphere up, we can see that once it hits the leaves, we have a collision being detected. Obviously, in the middle, we have a collision being detected. Perfect. All right, except for that one typo, I got that right on the first try. Wonderful. So you can see this is performing considerably better than it was before. Off the top of my head, when I was testing this earlier, axis align bounding boxes versus triangle meshes were giving me about, I want to say 15 frames per second, and spheres might have been a little bit better. Spheres might have been like 25-ish. You can see that now our FPS reel is hovering about 200 to 300. It's not amazing. Again, this is not perfectly optimized code. There are definitely some micro-optimizations that can be made that will shave off a couple CPU operations. Again, if we wanted to run this in the Yo-Yo compiler, I don't know if I should say again, I don't know if I mentioned that earlier, but if we wanted to write this in the Yo-Yo compiler, that's going to compile the game into C++. It's going to convert the GML into C++ anyway, and then compile the C++. And that should give us a further performance boost. I want to say such a thing should give us about a 2 times improvement in speed, and it's actually a fair amount better than that. We were getting 200, maybe low 300 FPS real in the GameMaker virtual machine, and we are now with the Yo-Yo compiler getting 6, sometimes 700 FPS real in the Yo-Yo compiler, which is a considerable improvement. See my previous rants about why FPS real is actually not that useful of a metric. Alright, that's wonderful. So if you want to, you can copy and paste this code and you can implement it for all of the other shapes. That is going to be a little bit of a pain in the neck. Copying and pasting code is generally a little bit frowned upon, especially when it's very, very similar code and it is maybe possible to come up with a general solution. So that's exactly what I'm going to do. I'm going to define myself a pneumatic static check general. That's going to be a function which takes any old incoming shape. Shape can be either a point or a sphere or an axis line bounding box or any one of these other things, except another mesh, really. And instead of on line 701 here and on line 707, instead of saying tree.triangles_i.checkSphere against the sphere, we can turn that around and we can instead say shape.check_triangle against the triangle stored at this position in the array. And down here on line 707, we can likewise say shape.check_ab against tree.childrenIndexI.bounds instead of doing a check sphere. And that is going to be our little general solution. This will work for any shape that has check triangle and check ab implemented, including other meshes. I recommend against it. Let's see. So what that means is that in checkpoint here, did I like... Oh, you know what? Alright. Almost moved the wrong code. In checkpoint here, we can say return self.check general against the point. In check sphere, we can say self.check general against the sphere. Same thing for the axis align bounding box. Self.check general against the axis align bounding box. When it comes to planes, when it comes to triangles.
Hey.
Meshes. I'm gonna say don't do this, but you know what? This is still not going to perform very well, even if it's accelerated, just due to the sheer number of math involved. But if you really want to, we can do a triangle mesh against another triangle mesh. Ray and line I'm going to leave for later. Those are going to be a little bit different because the raycasts are constructed a little bit different. I see we are building for the Yo-Yo compiler again. I'm going to stop that because the Yo-Yo compiler sometimes has issues when you run it more than once with code changed. I'm going to go back to the virtual machine. Let us create ourselves a tree, and let us go with a point. So checking points against triangle meshes is kind of useless because this only checks to see if the point is contained within each of the triangles. It does not check to see whether the point is inside the triangle mesh. Containment checks are a little bit different and also a little bit more difficult, and also a little bit, I'm not going to do that right now. However, spheres, as we saw earlier, spheres work. The general solution works for spheres. All right, that's awesome. Axis line bounding boxes versus triangle meshes. Let me move my mouse cursor over the way. We have collisions being detected up at the top, no longer. Over on the sides, we are barely cutting through one of the leaves of this tree. Out on the sides, we have collisions detected and not, and left and right. All right, great, wonderful. What next? Planes. Oh, that's a little triangle. All right, so we can also do individual triangles against triangle meshes again on the expensive side because triangle collision checks are on the expensive side. You can see that whereas the sphere was giving us about, let's say, 300 FPS real, this is giving us about a little less than 60. What was the ab giving us? That was giving us high 300s, sometimes 400. All right. the triangle still works, as you can see, if you move these shapes around. Ooh, wow. Well, that's still better than triangle, just iteratively checking every triangle against the tri-mesh. We're down to the 15s here. Anyway, what's next? Planes. Alright, I'm losing my controls here, but planes, check for a collision against the triangle mesh. That works. If I move the plane over the top of the tree, then the collision is gone. If I move the plane down below the bottom of the tree, the collision is gone. If I were to rotate the plane and move it around, it is colliding correctly. What other shapes are there? Lines. I do not like the way that I constructed my line tests, but if you were to... Oh, you know what? I didn't implement lines yet, did I? Alright, I'll do that next. Anyway, this is a fairly important milestone. I will be committing this. So first, raycast against collision meshes. This is going to look a lot like the other shapes against the collision mesh, in that we are going to make a queue of subtrees that we want to process, and then we're going to check each of the relevant subtrees for triangles against the ray. However, the raycast checks are just different enough from the other shape checks that a general solution is kind of going to be more trouble than it's worth. You could do it if you really wanted to, but it'll be ugly. So instead, I'm just going to copy and paste. There are two relevant lines that are going to need to change. Again, that is going to be here in the if tree.children equals undefined when we check each of the triangles against the incoming shape, in this case array, and also farther down in the else block, where we check the ray against the axis line bounding box that represents each of the octrees. For the first one, we can just use ray.checkTriangle instead, and since each of the raycasts collision methods use they take a second parameter for the hit info, so that we can use this to figure out relevant information about the point of contact, such as where it happened and what the surface normal of the thing that we contacted with was. When we say ray.checkTriangle, we are also going to pass in the hit info struct over here. We're also not going to return true, and the reason for that is because when you do a raycast, you generally want not only to figure out if a collision with the ray happened, but you want the information on the one that happened nearest to the ray's origin. So instead of just returning true, we are going to save the result. We're going to initialize hit detected to false. If you find a contact between the ray and a triangle, hit detected is going to be set to true. And also inside ray.checkTriangle, the raycast hit information struct is going to be updated. And then at the bottom, instead of returning false, we are going to need to process every triangle in the octree. We're going to return hit detected. And then when we check the raycast against the axis line bounding box, we don't really care about the hit info, but the raycast.checkAb method would like a hit info anyway. You can do one of two things. You can either go into each and every one of the hit info, each and every one of the check raycast methods, and you can do something along the lines of if hit info is not equal to undefined, and then you're free to ignore the hit info parameter to the raycast function down below, or you can just not do that, and you can instantiate, where was I? Check right. You can instantiate a dummy raycast hit information struct, which we are never going to use, but is just going to be passed into the checkAb method to keep the code happy. Let's see. This should work. Am I missing a close parentheses anywhere? I need... Alright, I am. Parentheses was in the wrong place. That should do it. Now, when I instantiate a triangle mesh, and if I were to zoom in and put my mouse cursor over it, you can see we have a raycast against the tree, against the collision mesh, and it's running at a solid at least 200 FPS real, depending on where you do the raycast into a more sparse or more dense part of the collision mesh. It may perform better or worse. That's the case for all of the collision shapes, but it's probably more apparent with the raycast. And you can see that the correct hit location is identified, the correct surface normal is identified, and we are also identifying the triangle that is nearest to the camera, as it should. Okay, and lastly, how do you detect collisions with lines? This is going to look an awful lot like some of the other line collision code, in that we are just going to use the check raycast as basically a springboard. We're going to turn the line into a ray. We're going to figure out if the ray hits the mesh at some point between the start and the end of the line. That's fine. So now if I run the game, we should, and despite the fact that which one was it? There we go. Despite the fact that my line collision detection test code is not very good at all, we can see that we do indeed have collision between the line and the triangle mesh. Alright, that was pretty easy. A lot easier than last time, honestly. Okay. That was fun. So we now have collision detection between triangle meshes and other things performing pretty well, all things considered. I still recommend not doing collision checks against triangle meshes if you can avoid it. If you absolutely have to, against, for example, terrain or a very, very strangely shaped building or something like that, then you can. Definitely would recommend using either a sphere or an axis line bounding box or a plane or something simpler if you can get away with it. Capsules are very common to represent things like the player and NPCs. I have not done capsules yet. I do want to later. I just I consider the other shapes a little more important because you can generally fake capsules with either two spheres or two spheres and an ab or something like that. There are other shapes that you might want to do. Cylinders, cones. Oblique bounding boxes, also known as oriented bounding boxes, just abs with rotation, are definitely something that I'd like to cover eventually, for reasons that are hopefully obvious. There's also the matter of applying a transformation to a triangle mesh, and I suppose applying transformations to other shapes before doing collision checks with them so that you can have things such as objects that move around the world colliding properly, but I'll take care of that later. That may or may not be what I decide to do next. And lastly, if you're wondering if you can apply the same octree logic to not only triangle meshes, but also just groups of other collision objects in general. So if you wanted to, for example, have a collection of abs in a game world, and if you wanted to sort those into an octree, the answer is absolutely yes, you can do that. And that's another thing that I want to do eventually, creating actual collision worlds that are more complex than just lists of collision objects. Anyway, I did both this and the octree video, last week's video, in one shot, and my voice is seriously starting to die today, so I think I'd better stop. My name is Michael. I like wizards and dragons and making games. If you want the code for this, look for the GitHub repository that I have been committing to in the video description. Look for I believe it's going to be week 17 using octrees release. I'll have a link to the particular branch as well. I have a Patreon, so if you want to contribute towards these videos being made, there are links to that in all the usual places. You can see some fun things like your name in the credits, or hear a verbal shout-out of yourself at the end of each and every one of these videos. I post a list of my future plans about once a month, and if you wanted to pledge, I would definitely appreciate it. Otherwise, I try to post about 1 or 2 game dev videos a week, so if you're interested in the weirder things that you can do in GameMaker, such as 3D collisions, feel free to subscribe. I hope you all found that useful, and I will see you all later. I forgot to include this demo again, so if you're wondering how the collision detection scales up with larger models, I want to say the going merry is about 2,500 triangles compared to the Kenny trees a little less than 500. So if you're wondering how this performs when doing collision checks against other shapes, you can see it is a little bit more expensive, definitely. We're getting a very variable amount of frames per second based on where in the mesh we're checking for collision with the axis line bounding box, but it's still definitely a lot better than when we were just looping through every single triangle. Worst case seems to be about 40-50 FPS real. Mesh against an ab. Whereas best case scenario, we can do a lot better than that. 100 plus, 200 plus, depending on where you're checking. Which leaves of the octree you're checking. I would expect to see more or less the same thing if I were to use the sphere, and we do. Okay. Other things you can do to optimize collision performance I will talk about later on in the series, but in the meantime, this is certainly at least serviceable. Special thanks to Army Armbuster, Edward Holt, Emily Koyo, GameMaker, Gunnar Clovis, Posho, Sindra Larson, Squarecrow, The Nothing Happened, Tusk, and Zenjamin for supporting these videos. If you want to see your name in the credits or hear yourself shouted out at the end, head on over to the Patreon page down in the video description to join the fun.